All right, so moving on to today's topic. Today's topic will be a gentle introduction to physics. So we will do no very advanced maths. Physics will be really simple. We will revisit vectors, absolutely. But first of all, this class today will be very much oriented into coding, okay? So we will code something. And what is it that we're going to code? Abdi, could you please mute your microphone because I can hear. Okay, thank you. All right, so what we are going to code. To show this, I need to share my screen. Okay, so you should see a goat running on snow. If you can't, let me know. All right. And right now I'm starting the first game we will be looking at in the physics part of this module. All right. Now I hope that you can all see a trolley on a inclined plane here. Drag the trolley and the triangular wedge, press space when ready. So we can drag this trolley, we can drag this wedge here, press space when ready. So what happens when we press space? This is a very simple physics-based puzzle. The goal is to catch the ball in the trolley, okay? Now I wasn't successful, so press F2 to play again. I can try and move this further. Okay, it now goes for a longer time. It's with even worse, all right? It's even worse this time. F2 once again, so I will move it down. If it goes from a very high position, it will gain in velocity and in speed. It will be faster. And if I move it lower, it will end up slower, and perhaps this is the way to get this ball. Let me see. Yes, success. All right, so this is one way to win. Another way to win is there is a small wedge here. This wedge increases friction from some points, so moving the wedge to the left can slow down this trolley quite significantly. Okay, and I won. So there are two different ways to solve this puzzle. We won't recreate the entire code of this application because it's not very complex, but it's a lot of stuff. I will concentrate on one thing. I will concentrate on the mechanics of this trolley. So there will be no ball present today, no these levers here. It will be just a trolley running down from a slope. Okay, so closing this, starting, because we will not start from scratch, but the first application, the initial application here, will be very simple with nearly no physics implemented. So this first application, just give me a moment, it's opened on the second screen, so yeah, that's the Visual Studio. When I run it, it doesn't do anything. First of all, space doesn't work, apart from telling me that it's simulating. So there is no simulation, no physics, no action. But there is the possibility to move this this trolley. But as you can see, the trolley is floating in the air, and moving it, it moves left and right, but not on the slope here. So there is a lot of stuff for us to be done. Now, looking into the source code, first of all, We have the main function, which is a very typical GFC main function, nothing strange here, apart from making this window a little bit bigger and changing the title of the screen, so nothing interesting here. My game class, open view code, no, F12, that's the definition of my class. So you can see a few additional variables here added. So first of all, I have the sprite trolley, the sprite called trolley. Then I have a definition of geometry, but to explain what happens here, I have a couple of slides for you. All right, so I will explain some concepts behind this code using PowerPoint slides, and then we will be building the code. So today's topic is playing and coding with laws of motion. But first of all, basic geometry. So that's the scene from the game. And now let's see all the measurements. So first of all, our floor, the flat the space on which the trolley rolls down, it's a number of units from the lower bottom edge, the bottom edge of the window, and this distance here will be called y floor, y coordinate of the floor. We also have a slope, and slope W stands for slope width. Okay, that's how wide this slopey area is. And one more important geometrical parameter of the situation is the alpha, is the angle at which this slope is located. Okay, so these three values can be coded as variables, okay, and our alpha is 30 degrees. Because we will be using a little bit of trigonometrical mathematical functions in it, I have provided this value of alpha in radians, okay? We have a standard, it's a part of standard C++ maths library, deg2rad, degrees to radians. So if I provide 30 degrees, then this macro definition, this, let's call it function, will provide me the value of 30 degrees in radians. There is another similar macro called rad2deg, which will convert from radians to degrees. So in other words, alpha is the angle in radians. We also have y floor set to 100, so you can see that our floor, the flat part of this configuration, is 100 units from the bottom of the window, and the slope width is 400, so this distance here is 400. And we indeed have these three variables here, alpha, y floor, and slope w. We also have two other variables that I don't want to explain in detail. They are for the direct manipulation functionality. So the function that allows you to click on the trolley and move it left or right, okay? The code for direct manipulation is located down here in the on mouse move, on left button down, and on left button up. So three main mouse functions. All right, and very briefly, if you click anywhere within the window, we check whether the click position, which is XY, is hitting the trolley, and if it is, we switch on a flag which tells that the trolley is being dragged. Is trolley dragged equals true. And we also provide the X offset. X offset tells us how far from the center of the trolley we have clicked, all right? And now each time the mouse gets moved, the program will check whether this flag is on, so whether or not we are in the mode of dragging the trolley, and if the click is within the range. So as if you start the application, you can see that I cannot drag it too far to the right or too far to the left. It's just limited here, so that's this condition here. And if this is everything is okay, then we set the x coordinate of the trolley to the x click position plus that offset that we have collected here. So it's a reasonably simple code, but this lecture today, this session today, is not about dragging objects and direct manipulation. It's about basic physics. So this was just one quick view into this part, and I will now go quickly to the physics part. And the physics part, maybe here, so a little bit of code structure. There is a number of fixed functions that are called in important moments in the life of application. So, for example, on display menu, this function is called each time you start the game, and also each time you press the F2 button. And here, two very important things happen. The first one is we set the position to 100, 400 for the trolley. By the way, it is its initial position, okay, as well. And we reset this velocity, set the velocity to 0, 0. What it means, when I start the application and move this trolley anywhere, then press space to get the simulation. Simulation doesn't work, but when I click F2, F2 will reset the trolley back to the original default position. That's this set pos here, set pos 100, 400. And also when we implement a little bit of simulation and the trolley will start to move across the window, then after pressing F2, you will need to set velocity to 0, 0. So these are two instructions that are already here in this code. We don't have to do it. Okay, so let's have one more quick look at this code. So this is a special syntax for initializing the member variables of the class, and we use it to initialize the trolley sprite. Okay, so the trolley sprite will be located at the coordinates 100, 400. That's these coordinates here. Okay, and the image of this trolley will be taken from trolley.bmp file. This file contains an image with a green background. Okay, we switch off this green background, so make the green color transparent, and in this way we have the transparency. Okay, so we have this sprite that is not necessarily rectangular. It is this, the trolley shaped in this case. And 0 is the current time, because this initialization happens at the very beginning of the application. We pass 0 there. So that's the construction of the class. Here is the onUpdate function, the function that is called 60 times per second, and its order is to the destination of this function is to update the state of the game at each frame of animation. So all the physics calculations will go here. The next function is OnRow, and this function is here. This function right now does everything that we need. Sorry, I have to switch it off. Okay, everything that we need in the image of this window. So these two lines, draw line, lines of code. These lines of code contain the draw line function that draws a line on the screen. and it uses our geometry functions, geometry values, to draw. The first line is starting at the x-coordinate 0, so it's left edge of the window, and the right edge is y floor, so the height of the floor, times slope w times tangent alpha. We have a little bit of trigonometry here already covered, but slope w is this value here. Okay, if we need to get the height of the slope, tangent alpha will give it to us. Okay, so Katoa, TOA, tangent is opposite over adjacent. The height is the opposite to the alpha. The adjacent is slope width. So slope height is slope width multiplied by tangent alpha. Simple trigonometry. You see, you have cases, nice situations in which trigonometry is really useful in programming. And the second point is just slope w, y floor. Slope w, it's this distance here. Slope w, slope width from the left side of the window, and y floor from the bottom. So that's this point. So this first instruction draws this line here. And the second instruction starts from slope w, y floor. So that's this point here, and draws until get width. Get width is the width of the window, which is in this case 1280 y floor. So it stops here. So the second line is simply drawn here. Then we have trolley.draw, so the function that draws the sprite depicting our trolley, and some messages that I will not analyze. They are quite boring, but working basically. All right. So on update, on draw, we will do a few modifications to on draw functions and a lot in on update because we have to implement physics in the on update function. So this function on update is where you by default put all your game physics. Okay, physics, this is graphics, and now initialization currently empty, but we will add one line of code here very soon. And on display menu, that's an important moment to do all the initialization work and to trust that this initialization will be repeated each time you hit F2 button, F2 key to restart the game. All right, so right now on display menu initializes the position and initializes the velocity of the trolley. This variable is just the initialization of the drag and drop system to move the cart across, and similarly here. All right. The rest of this code is not interesting for us, mostly empty functions, keyboard functions. All right. So, guys, if you have any questions, please send them to the meeting chat, or don't hesitate to interrupt me and shout your questions to the microphone as well. Because we will now move on to some stuff of initialization of our cards. So we've seen the geometry of the scene that we have, but now let's have a little bit closer look at the card itself. So this is how our card looks like. One thing that you probably noticed is that this card will sometimes need to rotate by 30 degrees, okay, or less than 30, or not at all, because whilst it's moving, it will be at different stages of rotation. So we need to rotate this trolley. Okay, that's the rotation. It's quite funny rotation because it rotates around the geometrical center of the sprite. So this rotation is always around this point. Well, the problem is that this point doesn't make any particular sense. This is just about the platform of this trolley. So After a few attempts previously, I found that there are actually two sensible, we call it the pivot points, the points around which the object, the sprite, can rotate. One would be at the basis, so somewhere here, but I found that it's even better to have this point, this pivot, just moved down to the midpoint between the wheels. Okay, wheels are absolutely crucial in the mechanics of this trolley. And first of all, we will implement today something that is called a wheel collider. Okay, so the entire movement of this trolley will be controlled by the front and the rear wheel. I will not implement physics of the trolley, we will implement the physics of its wheels. And therefore, the whole thing should be concentrated, focused on these wheels. So if we want to rotate this trolley, the best way to rotate it is to rotate it around the point which is 20 units. This is how the graphical image was drawn, all right? So the geometrical center of this image is 20 points, 20 pixels above the line connecting the wheels, all right? And in GFC, you can very easily move a pivot from the center. It will be moved by 0 minus 20. 0 because it doesn't change in the x direction. Minus 20 because it will go down along this arrow here. Okay, so we want this pivot to be here. And when this pivot is here, the rotations look much, much better. Okay, this trolley is now rotating around this specific point right in the middle between the wheels. Okay, so this is the code we want to implement. And we will implement it in the onInitialize function, the special one-time initialization function, because we just want this pivot to be moved forever. Okay, so we will do it in the initialization. Trolley. That's the first line of code we are creating today. Set pivot from center 0, negative 20. Okay, that's done. It won't change anything in the behavior of the application of the game because we just changed the pivot. We don't rotate this object, but everything else will be now easier to do. The next thing is to relocate this trolley. All right, we don't want this trolley to float in the middle. We want this trolley to be get down to the slope and also rotated. How to do this thing? So firstly, let's have a look at some geometry of our trolley. So first of all, the distance between the center of this of the wheels and the bottom or baseline of the wheels is also 20. Okay, this is basically because this image is 200 pixels by 80 pixels high, and the diameter of the wheel is 40, the radius of the wheel is 20. Yeah, so this distance here is 20. We will also need this distance, okay? The distance between the center and the rear wheel and forward wheel, front wheel. This trolley is ideally symmetrical, so both distances are exactly 60 pixels, all right? So we have some geometry. 20 here, 60 and 60. All right, but we want to place it on the slope like this, okay? So first thing is the position of this trolley. The position is defined by XY coordinates. We don't want to change anything in the X coordinate, all right? We're perfectly happy with the X coordinate. We just need to move it up or down to get the right height above the floor, okay? But even before doing this, we can write the first line of code, trolley, set rotation, rad to deg alpha. Rad to deg, we have to apply this rad to deg thing because GFC operates in degrees. And alpha, we have already converted alpha from degrees to radians. So now we are going back from radians to degrees. So it will rotate the trolley by 30 degrees. So that's the rotation of the trolley. So it will be rotated. Now, how about this y coordinate that we really need? Sorry guys, but the only way to do it is through some trigonometry. I told you that you will need trigonometry to program games. Okay, so we have a right triangle right here. Okay, this right triangle, if we know this distance here, this means that we will know the height of the trolley above the floor, and the position of the y coordinates of the floor is y floor. So the new y coordinate of the trolley must be equal to y floor plus whatever is the length of this. This is the opposite edge from the angle alpha. What we know, not too much at the moment. Slope W is the length of this entire section here. So from here to here. But wait a moment, we also know this position because we have a sprite, the trolley sprite, and we can ask this trolley sprite for its x coordinate. So using the C++ notation here, if we take slope W, that's slope W, and subtract the trolley get x coordinate, that's this distance here, we get the length of the adjacent edge of our triangle. Okay, so that's slope W minus trolley dot get x, the adjacent edge. Now opposite edge. If we have adjacent and opposite, which trigonometrical function should we use? Sine, cosine, or tangent? Waiting for replies from the chat. Tangent, very good, Yuan. Absolutely tangent. Tangent alpha is opposite over adjacent. So opposite, the one that we are looking for, is adjacent multiplied by tangent alpha. Okay, so it is all these things, slope W minus trolley get x multiplied by tangent alpha. And here it is. Sprites in GFC have a very useful function set y, well, set x, set y, and set pos or set position to set x and y at the same time. But we just need to have this y working. So that's it. Set y floor. Don't forget about y floor plus. We have to include this distance here. Plus slope W minus trolley get x multiplied by tangent alpha. Tangent alpha will only be multiplied to this expression in the bracket, not applied to y floor. So it's mathematically correct. To speed the things up a little bit, I will copy this code and go to Visual Studio and paste this code here. Okay. So we have these two lines, and we hope that they will put the trolley right on top of the slope. All right. So let's have a look. Nearly. nearly, okay, but not exactly. Rotation is good, all right? So it has been rotated 30 degrees, not a big surprise, but simply correct. Y is apparently close, all right? It's too close to be coincidence, but there is something missing. What is missing here? The answer for this question is quite simple. Oops, sorry. I need this slide. Okay, the answer for this question is quite simple. We have set the pivot of the trolley at the point between the centers of the wheels. If we did set the pivot at the point at the baseline of the sprite, this step would be easier because we would just get things done, right? It would just stand on top of the slope. But now, pivot is not only used for rotations, but also that's the point by which the all functions like set position, set x, set y normally work. By default in GFC, the pivot point is always in the geometrical center of the sprite, but in our case, it's moved down by 20 pixels, so it's 20 pixels above the baseline. All right, and I can see guesses here, plus 40 or plus 20, but not exactly. It would work if we were on the flat floor, but it's slopey, okay? So it needs to be 20, but this direction. Okay, you have already guessed that this is 20. I have a special animation to show that this is 20, all right, because we have this distance here, that's the 20, okay? So that's how much we sank into this slope, so we have to go up by 20. But the problem is that it is not 20 pixels up, okay? It's 20 pixels diagonally at alpha angle. All right, so how to find 20 times cosine alpha E1, that's a part of a good solution. I just would need another coordinate. And anyway, I will show you a little bit more vector oriented solution, all right? Because um, I'm not sure if you share the sentiments, but after the trigonometry test, it looked like you might have been overfed with trigonometry and looking forward for the vectors. I'm not sure if after the vector algebra test, you think that vectors are nicer than trigonometry. But I will tell you, absolutely you should. Many solutions, even if you don't think so now, when you eventually master vector algebra, you will discover that the world becomes so much simpler if you can describe everything in vectors, and vectors have a tendency to hide a lot of trigonometry. All right, but anyway, what I mean as vectors, okay, that's what we hope that this thing would do. Okay, so if this trolley is moving along this arrow is 20 units long, but at an angle, the trolley should stand on top of the slope. Okay, so we have this vector. This vector is, first of all, it is perpendicular to the surface. Okay. Do you know how there is a very special vector which has a very tricky name because it's very often confused with another type of vector. Can you guess what type of a vector we will be using to, yes, a normal vector. Yes, exactly. not normalized, but I will start from the normalized vector. Basically, what I'm going to do is to try and use this statement in GFC. Surely.move. Move is just changing the position of the sprite along a vector, along the provided vector. Okay, so this is a vector. Okay, if normal is the usual mathematically correct, so normalized normal. Okay, so it's a vector with the length of 1 and perpendicular to our surface. If I multiply it by 20, I move in the perpendicular direction, so I move away from the surface to the distance of 20 units from the surface. So that's exactly what we need. That's the instruction that we will use to move the trolley away from this surface by 20 units. And you know what? This instruction will work every time if you have any kind of a surface and you know the normal for this surface. I told you once that normals are incredibly important in graphical programming, and this is the case. If you know the normal, you can do it very easily. And how to know this normal? Okay, I have another slide. There will be more coding very, very soon. It's one of the last slides that I want to show you about the basic geometry of this thing. All right, so it's not to the scale, right? It's magnified just to make things clearly visible. So this is the normal vector. The normal vector has magnitude or length of 1. All right, we know this angle alpha here, and we can build another right triangle here. So sorry, that's the last moment of trigonometry here. We can build a triangle, and this triangle will have the alpha angle here. Okay, so if I have the hypotenuse of 1, the alpha angle here, then the sine of alpha will be equal to the opposite edge divided by hypotenuse, so divided by 1. Opposite divided by 1 is opposite. Okay, so opposite is sine alpha, and the adjacent is cosine alpha is the adjacent divided by hypotenuse, so adjacent divided by 1, so cosine alpha is the adjacent. So it's just sine alpha, cosine alpha here. And looking at this vector, we have ready to use coordinates of the normal vector for a surface. And this is a very nice thing, because if you have any surface, okay, and the surface is rotated by an angle alpha, okay, and the normal will rotate together with the surface. So if this is normal, this normal will always be sine alpha, cosine alpha. C vector is normal sine alpha, cosine alpha. All right. With this thing, we are ready to finish coding. So what I will do, I will put here C vector normal, and it will be sine alpha, cosine alpha. Yes, and let's say that we will do it here after setting the y, but before the rotation, we will move the trolley dot move by 20 times normal. Done. And here it is, standing nicely on the slope. I will go back to the code for just one more second. Scroll down here to mouse move function, and I will uncommon piece of code that was previously added here, but please note that the code very similar to what we have just done. That's also a normal sine alpha, cosine alpha, trolley set y, exactly the same thing that we have just done in the on menu on display menu function, okay, and move normal plus times 20. This is to keep the same thing, so keeping the trolley on top of the slope also in the dragging mode. All right, so now I can just take it and move it up and down, and it works quite nicely. All right, now we have done a lot of geometry so far. We will now do one more step because, as I told you, the mechanics of the trolley will be created by the mechanics of the wheels. All right, so we will be controlling the wheels, and then we'll just stretch the trolley in between these wheels. So what I need is to go to my header file. Okay. In the header file, I will add two more sprites. C sprite over front, comma, rear. Okay. Sprite oval because the wheels will be circular objects, and I don't care, they don't have to look pretty, because in the final stage they will be only so-called wheel colliders. Okay, what is a collider? Collider is an object in gaming that first of all exists, okay, makes some useful function mostly of checking for collisions, but also a lot of other physics related functionality, and colliders most often are invisible. Okay, our colliders will initially be visible. I will make them visible in a moment, but initially, finally, we will just see the trolley without these not very good looking wheels on them. All right, so let's go to the constructor. Okay, and I will excuse you for just a moment, because I will switch the finished solution on my second screen so that I can speed some coding operations up by copy and paste. If something is not particularly interesting, it's probably better to get it in one step like this, okay? So here we have the initialization of the front and the rear wheel. Please note, first of all, the coordinates, all right? The coordinates are based on this simple geometry, all right? Let's just imagine it's not rotated yet. The wheels are 20 points, 20 pixels below the original pivot of the trolley. One word of explanation here: when we construct them for the first time, the trolley doesn't have this pivot changed. Okay, so the wheels are 20 pixels below the trolley. So if the trolley y coordinate is 400, y coordinate of the front and rear wheel will be 380. Oh, sorry for that. Now, the front wheel is 60 pixels in front of the center of the trolley, and the rear is 60 pixels behind. So the initial coordinates are 100 minus 60 is 40, 100 plus 60 is 160. Then we have the size. So these ovals will be based on a 40 by 40 square, and they will be red. Okay, a simple thing. Okay, so now for any sprite to be visible in GFC, first of all, we should add an update function for front and for the rear. Sorry, and for the rear wheel. And now we will add the same thing for the drawing. Okay, so right now we have the trolley that is drawn, but I will just copy and but we need this to be drawn, not updated. When I run it, I should see the wheels. These wheels will float in the middle because they will be located at the initial position of the trolley. So the trolley is now sitting nicely on the slope. The wheels are not yet, but that's not a big problem. It's quite easy to solve. What I need to do is to go down again to the on display menu function where we had the code to put the trolley nicely on the slope. And now I will take the front wheel and I will set its position at the trolley position. Okay, that's not everything. It's just the first step, but that's the instruction which puts the trolley at the same position as, puts the front wheel at the same position as the trolley. I can do the same thing with the rear window, rear wheel. And what happens now? First of all, it looks like I had just one wheel, but it's obvious because I used the same position for both wheels, so they are occupying exactly the same space in the window. And they are right in the middle between the wheels, okay, because that's where we have chosen to put the pivot point of the trolley, and the pivot point for the wheel is of course its geometrical center. So the geometrical center of the wheels is at this pivot point. What we can do now to get these wheels put, one has to go forward, one has to go backwards. All right, so basic geometry, something very similar to what we did previously in order to rise the trolley up so that it stands on the surface of the slope. But now we need to use a perpendicular vector to the normal. Okay, this is the normal, and this would be the perpendicular. If we can only find the perpendicular vector for the normal vector, okay, this perpendicular vector times 60 will move the front wheel here, and multiplied by negative 60 will move it this way. All right, and now you remember question 2, I think I or J, near the end of the, no, sorry, not 2, 1 I, 1 J, 1 I or 1 J. I don't remember exactly which question it was, but we were asking in the test you to create a vector which is perpendicular to the given vector. Many of you did it, some of you didn't, but anyway, I will now create the perpendicular vector to the normal vector. I will call it x normal, okay? X because it's like a cross for the normal, okay? If I have a normal and the perpendicular, I get a cross. So x normal, and this x normal is created by taking the y coordinate of the normal, so normal dot y, and sorry, it is in GFC it's called m underscore y, and normal m underscore x. Apart from that, I need to put a minus sign here, and in this way I took the normal and I found the vector which is perpendicular to this normal. And now if I could use the move function, right? So it could be trolley dot move 60 times x normal, but I can also do a following thing. I can take this position here and just add. Okay, you can very easily add vectors to each other. Okay. So that's this power of vector-based programming. I have the position of the trolley, and I can just add to this position of the trolley my x normal multiplied by 60, and I can do the same here, but subtracting x normal 60. All right, so it will be moving 60 pixels one way or the other way in the direction which is perpendicular to the normal. And let's have a look if it really works. It should. Doesn't work. Okay, not a problem. I just have to switch the previous instance of the app off. Now it should work. Yes, it's working. It's working. All right. So the wheels are now located on top of the wheels of the trolley. The problem is that if I'm moving this trolley, the wheels are remaining in place, but this is another section of the on-mouse move predefined code. Okay. You can see that we also have created x normal here, a little bit different, not as a normal my minus normal mx, but directly by cosine alpha minus sine alpha. But then there is set position trolley correct position plus 60 times x normal and minus 60 times x normal. Now this should work nicely. All right. So now the only problem is that when I hit space, nothing happens. So time to start doing physics. All right. Closing the application. A very basic physics that we will be using in this part are actually the Newton is this guy here. The Newton's laws of motion. So he proposed 3 different laws. If no external force acts on a particle or all the forces are balanced, then the particle moves without any change in velocity. 2 things important here. It doesn't mean that there is...
You're not sharing the screen.
Oh, I'm not sharing the screen. Thank you very much. Now I'm screen 1. Now I'm sharing. Thank you for noticing this. So once again, I'm showing you Newton, okay, and Newton's laws of motion. The first law of motion. If no external force acts on a particle or all the forces are balanced, then the particle moves without any change in velocity. So important things are, it very rarely means that there are no external forces. Much more often there are forces that are balanced, okay? And the second thing, if this happens, then your object can stay at rest like Stonehenge, okay? If it was in rest, it stays at rest, but it also can be like Enterprise, it's just moving on, okay? And in space, when you get velocity and switch off the engine so there is no external force, you will just continue your movement on a straight line. That's what the first law of motion tells. If you are already in motion and you need to stop, there is a force necessary to stop you, all right? On the surface of the Earth, we are quite confident that everything in motion will eventually stop. Okay, that's not what this law says. Why it happens in practice? Because on the surface of the Earth, we either have air resistance or friction. Okay, if something is rolling, like our trolley rolling on the floor, there is friction. Friction is a force, and eventually it will make the trolley stop. If something is even flying across the air also has, it is not called friction, it's called drag or air resistance, but it also eventually would stop and drop down probably, unless it has driving force. So that's the first law. And notice that the behavior of objects around us is usually affected by air resistance and friction. And this illustration shows a case in which there is still friction, but not too much of this friction. So if you are skating, you should know very, very well that when you gain velocity, it may be quite a problem if you need to stop, okay? Because you need to apply an additional force to slow down and eventually stop. That's the first law. The second law is about the situation in which we have an unbalanced external force acting on an object. And in this case, the object will start to accelerate. This acceleration will be directly proportional to the magnitude of the force and in the same direction than the force. So remember about vectors and directions of the vectors. And it will also be inversely proportional to the mass of that object. We'll be not looking into the mass of objects today because we are doing a very simple example. And in terms of vector algebra, acceleration is always the same direction as the force, okay? So the acceleration will be just the force scaled, so multiplied by a number. And here you have two basic formulas. Acceleration, A equals force divided by mass, or its transformation, force is acceleration times mass. That's the second law, and this second law is visible, among other things, in the gravitational force. Gravitational force pulls everything towards the surface of the Earth, and anything that is within the gravitational field, so it is affected by the gravitational force, sorry, I'm trying to stupid thing. Sorry. Stop sharing the screen for a moment. All right, I have this pencil. All right, and when I drop this pencil, it drops down. Okay, and this movement is the accelerated movement. Okay, and this acceleration is called gravitational acceleration, and we will accelerate our wheels in a moment. Okay, but before we accelerate the wheels, I will go quickly to the next slide before proceeding to the third law of motion. Notice that the behavior of objects around us is usually affected by air resistance and friction. So if I have something very light and something very heavy, usually the heavy thing would drop down much faster than the light thing, but it is not the case that the gravity works more on the heavy thing. the acceleration, gravitational acceleration would be equal, okay? But the result of air friction, air resistance is much stronger in case of a lighter object than a heavy object. Okay, and the final rule, whenever A exerts a force on B, B simultaneously exerts a force on A with the same magnitude but opposite direction. Again, we have two skaters. It's impossible to push another skater without being pulled back yourself, all right? The same thing is also true in case of shooting. If you shoot, okay, if you have a pistol or revolver or gun or whatever, and you shoot, then there is a reaction force which in the moment of shooting will pull you back, pull your hand back. And we will use two or maybe all three rules today. So the first thing to do is to go to our code and this is the OnRow function when we draw the trolley, the front wheel and the rear wheel. And just to avoid distraction, I will comment out the trolley and comment out the rear wheel. Just checking my list of things that have to be done. Okay. All right. Yes, that's the right thing to do right now. So we will have now our game with just a single wheel. All right. But what I'm going to do is I will first model the physics for one wheel. Then I will add the physics for the second wheel, and then we will construct the trolley on these two wheels. By the way, I can still move it on because the trolley sprite is not removed, it's just made invisible. Okay, so yeah, space still doesn't do anything, but it will start doing something very, very soon. So we go to the onUpdate function. OnUpdate function that gets the current time and checks if we are in the simulation. So the simulation will wait for me to press the space button, and then it updates the front wheel and the rear wheel. But because nothing special happens with any of these wheels, nothing happens at all. You could notice, I hope someone noticed that, this code is missing one thing. We have the onUpdate function for front and rear wheel, but we don't have the update function. We don't have the update function for the trolley. Why is that? Simply because we will create physics for the wheels only, and the trolley will follow these wheels, so we don't need to physically update the trolley. All right, so first thing, I will create the gravity. And the gravity, of course, will be a vector, because in the physical programming, nearly everything is a vector. Gravity is a shortcut. It's a brief name for the gravitational acceleration vector. Okay, gravity. And it will be, this gravity will be 0, -10. Why? 10 is very close to 9.81, which is the real value of the Earth gravitational acceleration. It's exactly 9.81 meters per second square. What is meter per second square? I will explain in the lecture next week. Okay, we will get a more theoretical basis for this. Oh, my Alexa told something. Yeah, I didn't call her. So next week, but today the gravitational acceleration will be the power of 10 pointing down. Okay, so its y coordinates is -10, and down only, so not left, no, not sideways, so the x coordinate is 0. And now, to apply gravity to my front wheel, I will simply do something like this: front dot accelerate gravity. I use the gravity to accelerate front wheel. Run the application. All right, and now when I press space to start the simulation, something will happen. My wheel dropped down. Okay, F2 to show this thing again. Oh, it's now much faster. I will, if you have a result like this, okay, so when I start the program for the very first time, the simulation is very nice, but when I restart, the wheel comes back to its original position, but oh, it's terrible, terrible, terrible. What I can do, sorry, I have to leave my onUpdate function for a moment. Scroll down to onDisplay. Here is the initialization of the front and rear wheel, and I have to do something like this: front dot set velocity. So I will set the velocity to 0, 0, and the same thing for the rear wheel, set velocity 0, 0. And now it won't be anything like that anymore. So again and again and again. This is because the second and consecutive simulations already had the velocity set at the final stage of the previous simulation, so the wheel was already running very, very quickly. All right, but of course, this dropping down is not exactly what I would like to see. So, what I will do, if the wheel is standing on any kind of a surface, and gravity is actually depressing this wheel, this object, to the surface on which it's standing, according to the third law of motion, the surface will react, okay? Action and reaction. The surface will react by pushing you up, all right? So every one of you is now sitting somewhere, standing somewhere, lying somewhere, okay? You are affected by gravity. I am affected by gravity, all right? I am pressing with my bottom to my chair, with my feet to my floor, okay? If there were no reaction, so no force that my chair acts upon my, well, bottom, okay, and the floor acts upon my feet, I would just drop down, and I'm currently on the second floor, so it would be quite unpleasant. Fortunately, there is a reaction force pointing exactly upwards. So let's do this thing here. Front dot accelerate, again accelerate, but this time negative gravity. Okay, negative gravity, running the application, and after pressing space nothing happens, but actually we have a kind of very wrong at the moment physical simulation, because in every frame of this animation, of the simulation, the wheel is gravitationally trying to go down, and it is at the same time pushed up by the surface below it. But this works like this only on the surface which is flat, horizontal. Okay, our surface is diagonal, and what happens is that this reaction force only works along the normal, okay? Along the normal. So the next step must be to find out what our normals are. And we will have two different normals of the surface. Whilst the x-coordinate of the wheel is less than slope w, the normal is sine alpha cosine alpha. And then when the wheel is over the flat section of the floor, the normal is 0, 1. And the code for this thing is here. So I have created a vector normal. Sorry, it shouldn't say wheel, it should say front. Okay. And now, if the front wheel at x coordinate is less or equal than the width of the slope, then the normal will be sine alpha cosine alpha. But if it is not, the normal will be 0, 1. And now, the first use of physics, vector physics. Okay, what we will have here, we will produce or find the dot product of gravity and the normal. Okay, so that's gravity dot normal, but dot product is a value, a numerical value. So that's just the magnitude of the force that we are acting with. Okay, so to get it working, we have to convert this into a vector. So we will multiply it by a normal. Okay, dot gravity normal is a number multiplied by a normal by a vector, it is a vector. So that's the vector, acceleration vector of the force by which the slope is, of the surface of the floor is acting upon our wheel. Let's get it running. Miracle, it's just rolling down along the surface. It's not noticing the flat surface, and I will explain this in a moment. Why is that so? But you see, we have done this calculation here based on just pure physics, all right? We have the gravity, and if we apply the reaction force, that is called a normal force because it's always acting along the normal of the surface, okay, this creates a force which we sometimes call the sliding force, which just slides this object down along the slope, okay. I have to say I like this moment, okay, because we did some physics and we can see that this physics works exactly as we would expect from the real life. We don't check any collisions here, okay. We just applied two forces and the composition of these two forces created exactly the motion that we would expect to get here. But what happens down here? Okay, I will try to pause. At this moment, it should start rolling along the floor. It doesn't. It doesn't, even though the normal changed. Okay, I will tell you one thing. It's maybe not clearly visible from this simulation, but whilst the wheel was rolling down the slope, it was accelerating. It was accelerating because these two forces, gravity and the normal force, weren't balanced, okay, and made the object rolling down faster and faster all the time. But after passing this moment, this logic here change the value of the normal from sine alpha, cosine alpha to 0, 1. And from this moment, the normal force and the gravitational force are exactly balanced. So at least it will not accelerate anymore. Okay, it's just moving with the same speed all the time. What we are missing here? What we are missing here is a very simple thing. I will add a few comments here: gravity and reaction. And now we will apply a collision, because what really happens when this object gets here, it's a collision between this wheel and the surface of the floor. And this collision, I will do a bit of physics that I'm not going to explain in so much detail today, all right? But these are, again, 2 lines of code that will fix the problem. And these 2 lines of code, first of all, I am creating an x normal of a vector which is perpendicular to the normal vector. And I will apply additional force, which is the reaction to the collision. Okay, and this force is its value is the cross product between get velocity and normal, and the direction on which it will work is x normal. Now, a very important thing: this collision. You were supposed in the last test, in the vector algebra test, to calculate marbles bouncing off a wall. If something is bouncing off a wall, we call it an elastic collision. In this case, we have an inelastic collision. We don't want the trolley to jump and bounce from the floor. We just need to stick to the floor all the time, roll exactly on the floor. So this is so-called inelastic collision. This is going a little bit forward in terms of physics, but anyway, that's how we can calculate it. If we had an elastic collision, then instead of cross product here, we would have a reflection vector, exactly the same vector which you calculated in question 4 of your test. This is a perfectly inelastic collision, and the cross product is the right thing to do. Sorry, it should be, of course, front. And this should be front. Okay, so that's the complete physics for the front wheel. Switching off the previous thing. Complete physics for the front wheel. Yeah, it works. Move it higher and it will get a higher speed, and I can move it lower and it will be just very slowly moving across. Okay, now the task is to do exactly the same thing with the rear wheel. The problem with the rear wheel is that it means all this code to be written again, okay, repeated for the rear wheel, because the physics for the front wheel and the rear wheel is exactly the same. Instead, I will cut this code, go a little bit up here, create a new function, see my game state wheel, see sprite. This will be a reference to a wheel. I will start calling this a front. I have created a special function to update wheels. Okay, I will go to the header file and add this. Oh, it's already here. I've forgotten to remove it. Okay, so that's my function update wheel. Okay, I will use this front name, and Visual Studio has a very nice renaming option. I can rename the front to wheel. If you use this option from the contextual menu, it will change intelligently. It will change all the uses of the front variable with the wheel identifier. Apply, and we have wheel everywhere. Now, update wheel front, update wheel rear, and I will have also to uncomment drawing of the rear wheel so that I can see the rear wheel. So now I will see two wheels. Okay. Please note that I just moved the code to a function, okay, and called this function twice, once for the front wheel, once for the rear wheel. Run. Nice, until it hits the floor, okay. So far, it is running at exactly the same distance, so it's very easy to build a trolley on top of these two wheels. But when I start rolling here, basically the rear wheel gains higher speed than the front wheel. So what I will do right here in the onUpdate function, I will calculate the new speed, so it's not velocity, it's the, sorry, very sorry for this. It's the numerical value of the speed as the arithmetical average of the speed of the front wheel and the speed of the rear wheel. And then I will set the speed for both the front and rear wheel. Let's try if it works for us. Switch off the previous. Brilliant, that's what we needed, okay? Basically, the rear wheel is faster than the front wheel. It will be delayed, it will be slowed down by the front wheel. And the front wheel, which is slower than the rear wheel, will be pushed forward, so sped up by the rear wheel. This is not exact physics, okay, but this is a brilliant illustration of something that we do in gaming quite often. Even if something is not the exact physics, it looks for me good enough, all right? The players won't see the difference, so sometimes it doesn't make a point to create a very complex, sophisticated solution if much simpler solution is probably faster, less prone for errors, and it's very nice because it works. It just looks good. Well, 4 lines of code from the success. The first 2 lines are here. I will look for the position of the trolley, because what generally we want to do, let's remove these lines. I want now to animate the trolley. If I just uncomment the trolley drawing function, okay, the wheels are going forward, the trolley stays at the same place. So what I will do, the position of the trolley is, again, the arithmetic average of the positions of the front and the rear wheel. And the ingenious thing about vectors is you can find an arithmetical average of 2 vectors, and this is the point which is exactly midpoint between them, okay? So if I take the position of the front plus position of the rear wheel divided by 2 and set it as the trolley position, I get this, and it's nearly good. The only thing is that I need the trolley to be rotated. And this rotation is not just 30 and 20, because, for example, at this position or this position, it's something in between 30 and 0, okay? 30 and 0. So what I will do, I will calculate your favorite displacement vector. Displacement, so the relative position of the front wheel in relation to the rear wheel. And I will do a very short trigonometrical function, okay? Because we are running out of time, I will not explain this instruction. A tan 2 is basically the opposite to tangent, so my divided by mx is supposed to be a tangent of the angle, okay? And we find the angle for which the opposite is y, the adjacent is x, and we set the rotation to the trolley. And this is nearly the end. It looks good. I will just change one more thing. I will comment out drawing the front and rear wheel because they are only the colliders, all right? All physics has been calculated for the front and rear wheel, but they don't look good, therefore they won't be visible in the final version. In the final version, we only have the trolley. And a nice simulation. I can put it up and get it running quickly. I can put it down and get it very slow. Guys, thank you very much for participating in this session or for watching if you are watching it online. Thank you and thanks for watching. Bye.